Hello and welcome to the course of Advanced Control Systems. So this course consists of ideas in control systems which are termed as modern control systems, and they go beyond what we have already studied in our first course in control systems, which were the ideas of transfer functions and transfer function models of systems, how to analyze those transfer functions for determining their stability and determining the response of the system. So those things we had studied in great details in the first course of control systems, and they are still very relevant. We also studied about compensators and controllers like PID controllers. We also studied about filters. So though these concepts are still very relevant, because a lot of systems, a lot of industrial systems can be modeled, a lot of process control systems can be modeled as first order or second order transfer functions. And when we model them in that manner, much insight is revealed from the system. So we can actually analyze the practical system using the analysis of the transfer functions that we already have learned about. And although it is true that the transfer function models are models and not exact practical behavior of the industrial plant or whatever system we are trying to model. However, they are very close, and it also reveals it reveals good amount of insight about that practical system, and we can be very sure of how we can manage the output of that practical system, whether we want stabilization or whether we want regulation or tracking. We can go ahead and do that with almost 100% confidence level. So that is the beauty of control systems also. So any control system is like that. So we can get from the practical system a desired behavior um, by studying the mathematical model of the practical system. So we don't always have to do the experiments on the actual system, but we derive, or we obtain, in some way we obtain a model of the practical system, then we analyze that model. So this analysis happens in pen and paper, in simulation, and we become certain that the model works in a certain so and so way, and we can control it in so and so way. So we can also we become certain that the real plant, the practical plant, will also behave in the same manner when we supply the same inputs to that system, to the real system. So transfer function approach was one way of understanding the system, the response that we obtain from the system, and understanding the behavior of the system in terms of stability and frequency response, time response, all those things. However, the transfer function is not enough. Why I say that that the transfer function is not enough, and we need to understand this very well, because why we are moving ahead of transfer functions, requires to be understood, so that we don't really uh, um, cling to the past, sort of what I can say. I can use this phrase maybe. We should not cling to the past, we should move ahead and look into the future, what the modern control concepts have to offer. And for that, to do that very in a strong way, we must have this idea in much certainty, that the transfer function approach, though it analyzed a lot of things, it revealed a lot of things about the system, but it is not enough. That means it has its limitations, so we need to understand its limitations before going ahead into the modern control concepts. So the some features we must discuss. So it has a simple design. The transfer function approach has simple design and analysis tools. They are very well established and they give a deep insight to the system. It greatly aids in preliminary system design also. So if you have a very complex system, you might consider to just build some transfer function and design for it, and then on top of that design we can add some modern control ideas, and complement that design. So and the fourth point that I figured out, or I found this from several books I collected. So the fourth point is this, that the system response can be predicted with the knowledge of response of a few basic input signals. So you can understand this very well, because if you remember, in the first course of control systems we studied the system response for step input, for a sinusoid, for ramp, for an impulse. So only a few basic inputs. And why so? Because most of the signals that we supply to the system would be composed of these signals. So when they are composed of these signals, we can write the entire input signal as a addition or a summation of these basic components. And transfer function modeling is basically a linear system design. So it works on the assumption that the system behaves in a linear manner. So that means that the system output would basically be a summation of the responses of those individual input components, input signals. So if you, so I am just trying to say this, that if you have your u as u1 plus u2 plus u3, and what I am saying is that these u's are what we studied, like maybe u1 is a sinusoidal signal, u2 maybe a square wave or a step input, u3 maybe a ramp input or a impulse. So impulse is not generally a practical signal. So these three are some the practical signals. So this u may be a combination of these, and there can be several other such signals also. So all the combination gives rise to u, and you know this, that a periodic signal, if we have a periodic signal, it is a mm, it is just summation of sinusoids. So there is one gain and the rest are the sinusoids. So so it is like that. So this is what I am trying to talk about. So we know the response of the sinusoids, we know the response of a step input. So the output, so the output y would basically be the summation of the outputs. Why? Because we have a linear system. So the transfer function is a modeling of considering the system to be behaving in a linear manner. So if the input is a summation of input components, the output is a summation of the corresponding responses. So that makes it easier. That enables us to only keep in our repository the knowledge of response of a few basic input signals, and with the help of that we can construct the knowledge construct the system response of any linear system. So that is a very powerful thing to have with us. However, the limitations are also there. So this thing that it is a LTI system only, so that is in itself a limitation. So this consideration that the system behaves in a linear manner and linear time invariant manner is a limitation in itself. And the other limitations are that it is defined, the transfer function can only be defined under 0 initial conditions. MIMO case is cumbersome to use. You may not have been exposed to MIMO transfer functions. So it basically takes up the shape of a matrix where each element of the matrix is one transfer function. So we don't need to go into that. So that is even not part of this course. So MIMO transfer functions are cumbersome to use. We also don't have any information of the internal states. So this is where our investigation will actually begin when we go ahead into the modern control concepts. But what are internal states, perhaps you are asking yourselves now. So it will be revealed to you, but let's know this fact that with transfer functions we don't have access to the internal states. So if there is something called internal states, you can very well understand that the transfer function does not give any knowledge of it, because what is the transfer function? It is simply a ratio of output to input. So you give the input, you obtain the output. If there is something inside, some other variable, you don't have any access to that, and you can't even predict, can't even have a handle to the behavior of those variables. So those variables basically called the internal states. We will shortly study them, just know about them. So it is only output based controller design, because we only have access to the output, and we cannot design the controller based on any other information. We have different transforms are there for continuous and discrete time systems. So in transfer function approach, if we want to represent a continuous time system, you have to go into the S domain. You have to go to the Laplace transform in the S domain. And if you want to represent a transfer function of a discrete time system, perhaps you are not familiar with the representation, transfer function representation of discrete time systems yet, but you know of the Z transform. So we have to go to the Z transform domain. So for representation of continuous and discrete time systems, we have to use different transforms. So that is also a limitation. One can consider it as a limitation, because in the modern control systems, we would just now we would start beginning to study the state space representations, state space realizations. So in state space realizations, the structure or the representation remains the same, be it continuous or be it discrete time. So the mode of representing the system remains the same. Of course, there are differences because one is continuous and the other is discrete. However, they are quite similar, so we don't have different transforms associated with them. We have the same sort of representation, and the techniques that we use are also similar to analyze the continuous time and the discrete time. The techniques that we use are also quite similar. So why this is why this is important? So I am highlighting the this fact. I will highlight this: no information of internal state. So from here we will begin our investigation. So why this is really a drawback? Why this is really a limitation? Also, this is a limitation. So I have already highlighted them with red. So again, stressing on this. Let us first just have a observation on the zero initial condition case. You must understand that not all the systems are starting from zero initial condition. Zero initial condition means that they are not having any internally stored energy. So everything is at rest. Then from outside you supply some input signal and it behaves in a certain way. However, it may not be always like that. The system itself may have some initial conditions, may have some energy within itself, and on top of that you are giving some external input. Maybe you don't give an external input, you just want to observe that if the system has some initial energy, what would happen to the system. So this sort of analysis, this sort of investigations is not possible using the transfer function models, because the initial conditions have been considered as zero. So that is the limitation. The next limitation: there is no information of internal states. Why this becomes important? Let us see this video. So this is a mass spring damper system with two masses, and as you could see, so let's suppose that the position of the blue mass, so here it is referred to as cart 2, position of this cart 2 is the output that I am concerned with. So looking from the transfer function model perspective, what happened here is that we gave some force, or we let it move from the some state initially, and we observe the blue position only. So if we are looking from the transfer function perspective, you have information of only the cart 2. However, of course, the cart 1 is also moving. So there is an internal state. So this is an internal state which is hidden when you only observe the system, or when you only study the system from with the transfer function model. So this real state remains hidden from us, and it might so happen that this blue are the blue lines are the springs and the green lines are the dampers. It might so happen that the force generated on one of the spring is so large that the spring might break. It may so happen, but we will not have any idea if we are only studying the input output behavior and then let the system work based on that behavior. So we are not having the complete knowledge of the behavior of the system, and we may have supplied that input signal and then just the system went boom. something broke inside the system, because we don't have knowledge of the internal states of the system. So that's why the knowledge of internal states of the system is very important. Perhaps this particular example is more close to your experience. I am not sure how many of you have burnt a resistor or damaged a capacitor or inductance in our labs, but if you have done so, you might you might you might like have a more closer understanding of this particular simulation. So what we are trying to see here, so you see a RLC circuit. So this is an RLC circuit here. So this is an RLC circuit here, and we are giving some input from here, input voltage. This is a current sensor, and these are the voltmeters across each of the resistor, inductor and capacitor. So again we'll play this. Sorry. So you can see that I just have given an input which is here in the step input of 10 volts for a certain duration of time. So the plot at the bottom is input output plot. So output here is considered as the capacitor voltage output. However, there are so many other states: the internal current I, the voltage across the resistor, voltage across the inductor, voltage across the capacitor. So all these are changing with time, but from the transfer function point of view, we are only studying the input output behavior. That is, we have only supplied a input of 10 volts for a certain duration of time. So it is like a square wave, and not a square wave, just a rectangular pulse, and we observe a output. So this output could be predicted very well by the transfer function model. However, these internal dynamics cannot be predicted. So what is the voltage across the resistor, what is the voltage across the inductor, what is the internal current in the system? So it might so happen that the internal current becomes so large that the resistor burns. So maybe it is a very small resistor, very weak resistor. So it like a fuse, it burns maybe. So we need to take care of that. So we need to understand what would be the internal current. So we need to have a knowledge of the internal state of the system. Similarly for VR and VL, so maybe some voltage across the inductor will do damage to it if it crosses certain limit. It might so happen. So those things we need to take care of, and for that we need to have a knowledge, have a knowledge of that, of how these internal variables will behave. So these are real internal states, so real internal variables within the system, and these internal variables are actually termed as states, though states may not be only restricted to the real internal variables, to the practical variables within the system. States as such may not always be the practical variables within the system. However, one can easily define a state with the help of these variables, with the help of these practical variables. So we can say, yes, one state is the current, another state is the voltage across the resistance, another state is the voltage across the capacitance, another state is the voltage across the inductance. So these are my states, I can say, and my output is the voltage across the capacitance. However, here you might notice that all these four independent quantities: the current, voltage, VR, VL, VC. All of these are not independent quantities, right? So like if we know the current, then the resistance is easily known. Not the resistance, the voltage across the resistance. So I and VR are directly related to each other, have a direct relationship with each other. So they are not independent. So knowing one of them is sufficient. We don't need to know the other. So in that way, we can say that only one of these can be considered as the state. So if we know that, the other variable can also be predicted. So states, when we define states formally, we will see that there is a term which is minimum. It will be defined as the minimum number of internal variables, like that. So it is the minimum set of such internal variables which we need to consider in order to understand the complete dynamics of the system, not just the output dynamics but the complete internal behavior of the system. So the minimum number of such variables is the collection of states. Another example we will see. So this is the cart pendulum, inverted pendulum on a cart. So this is an unstable system by nature. However, the first example that you will see is having a closed loop controller, so it will be stable. So the problem is to move the cart from one position to another, keeping the pendulum upright. So you see, now since the controller is already implemented, this moved from this position to this position with maintaining the pendulum vertical. Again it will move back, maintaining the pendulum vertical. So here you can see in the plots, so the yellow line is the reference position and the blue line is the cart position, actual cart position, and orange is the pendulum angle in radians. So as you see, the pendulum angle becomes 0 once more. So there is a certain deviation as we start to change the position, but then it again becomes 0. Now if your cart position is the output without any regard to the pendulum angle, then what will happen? You can say, okay, yeah, my cart will reach here, the pendulum will fall down, but the keeping the pendulum upright is the nature of stability of the entire system. So you can't have the pendulum fall down from the vertical position. So there are many practical systems which depend on this particular philosophy of the inverted pendulum. So inverted pendulum is studied as a model system. It is a model system of a lot of different other systems. Like you can consider you're riding the bicycle. So the bicycle has to stand upright even though it moves from one place to another. You cannot fall down, right? So the pendulum cannot fall down while it moves from one place to another. So these things are all having the idea of inverted pendulum in a cart. So the inverted pendulum in a cart is a very well studied system. So the next we will see the same inverted pendulum in a cart where the controller is absent or maybe faulty. So it is like a novice or a child trying to ride a bicycle. At one point of time he will actually fall down. So we when we have started learning bicycle, once in our life we have fell down, and then we realized how to balance ourselves. So what happens here, you see, the pendulum will fall down and also the cart will go somewhere else. The cart does not reach the position intended to. So even though you thought that the cart will reach at the position intended to, it doesn't reach there, as the pendulum becomes also unstable. So you cannot achieve what you wanted to achieve from the system. So the internal state matters. The knowledge of the internal state matters, and the analysis does not become complete unless you analyze and unless you take into account the internal states. So that's why the internal states are important, and this is a serious limitation of the transfer function method, along with the limitation of being modeled with zero initial conditions. So the state space realization, which we will start talking about now, takes care of both these limitations. So it is not restricted to zero initial conditions. As you can see, it is not restricted to zero initial conditions. It is also, the internal dynamics are also revealed. The internal dynamics are obviously revealed because we are terming this as state. So the states are the internal dynamics. Basically, states are the minimum set of internal dynamics we need to know in order to completely describe the system. The formal definition will be put. So I am just saying from my own mind and experience, like, so the formal definition will be shortly given to you. It is also in the slides. So other advantages, it works for linear, non-linear, time invariant, time varying. All classes of systems can be represented with state space realization. So this model, the modeling in the state space models or the state space realizations, state space representations, all these mean the same thing. So they work for all classes of systems. Whatever class of system, they work for all of them. You can represent them in state space relations. So I guess I have not missed, but overlooked this, and this point will be very evident, that it is a time domain approach, whereas transfer function is a frequency domain approach. So in transfer function, we need to transform the system, which is basically a time domain thing. The system works, the system gets evolves with respect to time, correct? However, we do the entire analysis in the frequency domain when we are looking for transfer function models. We don't need to do that for state space relations because they are in time domain. So they are models in time domain. So direct understanding of the response of the system, direct understanding of the behavior of the system in time domain takes place. We don't need to go to frequency domain and again come back to time domain. It is a generalized representation for CISO and MIMO. So even if it is a CISO system, its representation is the way it is represented remains same whether it is a CISO or a MIMO. Both state and output based controller design is possible. So since we have knowledge of the states basically now, so the states get revealed in the state space models, so we can design the controller using the states also. Same representation for continuous and discrete time. So these are the pluses. So these are the features which make it superior to transfer function modeling. There are some additional features. Additional features, it's a direct, yeah, I mentioned this. So it is a direct time domain approach, not needing any inverse transforms to obtain the response. Easily lends itself for computer based numerical calculation. This is also an important feature, because in modern control we are using the microcontrollers and other computational devices to calculate the control action. So everything is happening in that digital hardware space. So we need to be in a domain which lends itself easily to the computer based numerical calculations. So these state space models are very easily can be very easily adapted to that. As you look into the state space structure, you will be able to understand it. So let us go ahead and see how it looks. So this is the comparison between the way transfer function looks and the state space relations look. So this is the mathematical structure. Transfer function we already know, there is a numerator polynomial and a denominator polynomial, both in the S variable, which is the complex frequency variable. We can also represent as in a pole zero form. So this is all we know, and the feature is that the output response can be predicted based on the input signal, but for LTI systems only. State space relation is what you see in the right hand side. So this is something new that you are looking at, and you need to understand it closely. So this is a general state space representation. So if we have identified n number of state variables, like in the previous examples we saw, we could identify certain state variables in the physical system. So in that manner, if we are given any physical system, we will be able to identify certain state variables in the system, certain numbers of state variables in the system. So if it is a nth order system, we will be able to identify n number of state variables. So we know what is the order of the system. Transfer function also tells us about the order of the system. So it is the same order that I am talking about. So if the transfer function is of n order, the state space realization will also be of n order, and there will be n number of states. So x1 to xn are the n states. So in the state space realization, we model the dynamics of each of these states. So generally it is modeled in the ordinary differential equations with the first order ordinary differential equations. So x1 dot equals to something, x2 dot equals to something, x3 dot equals to something, and in this way xn dot equals to something. So these are the first order ODEs. So first order ODE, ordinary differential equations. Though the system is of nth order, each states are modeled in their first order ODEs. So the dynamics of the states are modeled in the first order ODEs. So this is something important to note. So if we have a state xi being the ith state, then we will have an equation which is called the dynamics of the xi state, and that equation will be like xi dot. So it is the first order ODE equals to some function of all the states. You see here xi to xn, xi to x1 to xn, as well as all the inputs which are available in the system, u1 to um. So if there are m number of inputs, so this function is the function. So in the right hand side, so the dynamics is like this. So x1, suppose I am talking about x1 dynamics is a function of all the states and all the inputs present in the system. It is in general a function of all the states and all the inputs. For one specific system, for some specific systems, this function might not contain all the states as the argument and all the inputs as the argument, but in general it is always possible that the dynamics contain all the states as its argument and all the inputs as its argument. It is possible. So we keep the provision in the general representation. We keep the provision in some specific representation, in some specific state space forms. We will find that x1 dot does not depend on all the states, does not depend on all the inputs. So in some specific form we will find that. However, this is the general form that I am talking about, and in this general form, this f1, f2, f3, fn, they can be any nonlinear function. So it might so happen that suppose I am talking about this xi dot may be, so suppose it is x1 dot may be x1 square plus e to the power of x2. It can be like this. So it is a nonlinear function. If it is a linear function, then simply c1 x1 plus c2 x2. It is simply linearly related to the states. So it can be linear, it can be non-linear. It doesn't have any restriction in this general representation. So the general structure takes care of all sorts of systems. That is what I wanted to highlight. The outputs, you can see, the outputs are simply algebraically related to the states and the inputs. Y1 is a simple algebraic function of all the states, all the inputs in general. So it might so happen that y1 is simply x1 plus x2. It might so happen, just depends on the two states and maybe some input. However, in general it is a function of all the states and all the inputs, and it is not a dynamics, it is a simple algebraic relation. Y1 equals to not y1 dot, y1 equals to h1 x1 to xn, y1 u1 to un. So only we are dealing with dynamics of the states. So we are talking about the knowledge of how the states are evolving. So this knowledge should be available to us. We are modeling that knowledge. So we are modeling that idea or that knowledge that we have from the system on how the internal states are evolving with time. This is what we are modeling. Of course, this x1 dot or x dot as such, you know this, that x dot, what does x dot mean? Any variable, if you take a dot, then what does it mean? It means that it gives the knowledge of its velocity, right? So if that variable is you term it as position, then its dot represents its rate of change with time. So we can term it as velocity maybe. So if there is a temperature, suppose, then if we take a dot, it means the rate of change of temperature. So in terms of control systems, actually we can say that this temperature is simply represented as x. So we can say that this is a position. So it is not a real position as we know in mechanics and all, but it is the variable in its basic form is sometimes termed as positional variable, and its derivative is termed as the velocity variable. So here also we can see we we have the knowledge of the velocity. So we have the knowledge of the rate of change of the internal variable, all the internal variables. We know the rate of change of all the internal variables. So what does this mean? Let us see a picture. So suppose you have a two-dimensional system. x1 and x2. So at any instant, your internal variables, forms a vector, right? X equals to x1, x2. This is the vector it forms. So that means it is any position in this space. So this is the x1, x2 point, and this is the vector x. So this is the vector x. This is x1, this is x2. Correct? So what does x dot give us? X dot. What does x dot in principle gives us? What does it mean? It means that this vector, this point, is changing its position. Maybe from here it goes here. At a very small instant of time, it goes from here to here. So this is the new position of x, and this is the direction of x dot. This is the direction of x dot. So at each instant you will be able to understand in which direction my vector should move if you have a knowledge of x dot. So x dot can be calculated because this is a known function, this f1 and f2. So f1 of x1, x2, f2 of x1, x2. So this is a known function, this is also a known function. So you can calculate what is x1 dot. So x dot is basically x1 dot, x2 dot. So you can calculate what is my x1 dot, what is my x2 dot. You can calculate. Suppose this is what you get. So you get a effective, so I have not drawn it very well, so let me change this drawing. Suppose this one is small and this one is quite large. So now the effective x dot is in this direction. So that means you are crawling up probably like this. Here you have crawled up. So you move from this place to here, and immediately when you move here, so I have moved a very small distance, because immediately when you move here you will get another x dot, because all these x1, x2 positions have changed, right? So here you will get another velocity direction. So by tracing the velocity directions, you can plot the entire trajectory starting from this point, rather starting from any initial point. So from any initial conditions, you will be able to trace the entire trajectory of the system, because you know what x dot is. So that is the model. From the model you are getting x dot. So suppose my trajectory becomes like this. It might so happen the trajectory is like this. So you can calculate this beforehand. You can calculate this. So this happens in the state space. So these internal states, suppose there are two states in this system. So these two states are plotted in orthogonal axis, and this gives rise to a space, a two-dimensional space. In this two-dimensional space, I can keep plotting the x1, x2 values as time evolves, and I can start from any position, and as I have already shown you, with the knowledge of x1 dot and x2 dot, I can figure out what my next position will be. So in that way I can plot an entire trajectory within this state space. So if it is 3-dimensional, there would be 3 orthogonal axes. If it is 4-dimensional, 5-dimensional, or rather n-dimensional, there will be n orthogonal axes, x1 to xn. So in our normal imagination, or what we see around us, we can only imagine up to 3 orthogonal axes. However, in mathematical domain, there can be any number of orthogonal axes. This is the mathematics of vector algebra, or matrix, or the mathematics of your matrix computation. So in general it is termed as linear algebra and vector spaces. We are dealing with vector spaces. So this x1, x2 to xn forms a vector, and this space that has been drawn with the axis x1 and x2, so this entire white slide you can consider as the two-dimensional vector space. So there can be 3-dimensional vector space, there can be n-dimensional vector space. Going ahead, normally we will not look back into this picture of the vector space. However, I urge you to keep it in the back of your mind. We will do computations, we will do algebraic calculations using matrix theory, using the computations between matrix and vectors. We will do that. However, you have to always keep the picture in mind, because only if you have a picture, you really have an understanding of the maths. Otherwise, only you are doing some addition, subtraction, multiplication, division. You are only being a computational machine. The machine doesn't have any idea of the vector space. So you should have an idea of the vector space. That's how you will become more than a machine, and you will reach closer to how these things had been formulated. These all maths has been formulated. They have been formulated from such geometrical ideas, and they work really well. So if you have a picture in your mind, be very sure that you have understood the maths. It might so happen that while doing matrix calculation, you may be doing it wrongly because of some silly mistake. But if you had the picture in your mind, that silly mistake does not should not worry you, because you should know that you understand the maths. Understanding the maths is more important. That's why I showed this picture. So this from this we again conclude. So I conclude and I go back to the slides. So the conclusion is that with the state space representation, we can compute the entire trajectory within the state space. The trajectory is within the state space. Correct? The state space is not something that we observe in the system. In the system, we observe, like in the pendulum system, we observe the card moving and the pendulum staying upright. The same thing when you plot in x1, x2 by calling x1 as the card position and x2 as the pendulum angle, you will get some different picture. That is the trajectory in the state space, which is an abstract space. You remember from digital electronics course, I talked about abstract spaces, mathematics, all these things. They reside in some abstract level of truth. They are there. However, they are manifested in the physical world in a different manner. So the manifestation we see, we observe. Manifestation we observe. However, when we want to analyze them, analyze this manifestation, whatever physical behavior we are observing, we have to go back to the abstract space and analyze it there. So that analysis, I showed a small bit of analysis, what is happening. So we can create the entire trajectory within the state space, and from that trajectory we can understand many behavior of the system. That slowly we will go ahead, and but you have to keep this idea in the back of your mind, that there is a state space and there are trajectories getting evolved in that state space. From the knowledge of those trajectories, the position of the vector x at each and every point in time, I am actually concluding things, I am making conclusions about the real system. Suppose I want to say what is the output. So the output is y equals to x1 plus 2x2. Suppose this is the output. This is how the output is defined. So at any position of x, you know what is x1 and what is x2, and you can easily calculate x1 plus x2. So you can get the output. So you can predict the output. So the internal states are getting predicted as well as the output is getting predicted. Whereas in transfer function, we can only predict the output. You have no idea how the internal state trajectory is getting evolved. So we will talk about the state in a combined way from now on. Actually, state as a state vector, not the individual states. Of course, the state vector is comprised of the individual states. Only when we know what are the individual states, or in some way we identify or we define the individual states, only then we can form the state vector. But once we form the state vector, our understanding must happen in a combined manner of the entire state space, not just one single state. Okay, so we move on, and this is the block diagram structure. So we saw the mathematical structure, this is the block diagram structure. Same thing, and here actually we come down from the general representation of the state space to a specific representation of the state space, which is the LTI, and this structure is very important for you to remember. This is with what we will work throughout the course. The linear time invariant single input single output case. In the scope of the course of UG third year, we will not go beyond this, and even within this there is a lot to explore. So that exploration we will do, and if you take up further control courses in your fourth year as a specialization, you may come to experience nonlinear. So nonlinear is there a bit also in this course, so that will be covered, but there will be some advanced level discussions about control systems if you take up some special paper regarding that. However, for the purpose of this course, we will restrict ourselves to state space relations of this form. And this is very simple, and it should be very easy for you to remember. You should remember this: x dot equals to ax plus bu, y equals to cx plus du. X dot equals to ax plus bu, y equals to cx plus du. So this is the state space relation of LTI CISO. Transfer function you already know, so I'm not going into that. And how you represent this in a block diagram structure, you note this. So as soon as we have included a dynamics x dot, we have to include the integrator, because only an integrator will give us a scope to create the x dot at the input side of the integrator. At the output of the integrator, we consider the state x. So this is also important. This is a general thing actually. So if you have identified states, of course there is a dynamics of that state. That means x dot equals to something. So when you talk about x dot, you can always represent, you can always put that x dot at the input of an integrator and put the x at the output of the integrator. So any state space realization can be represented in a block diagram using this method. So you just identify how many states are there, those many integrators will be there in the block diagram. This is also a quiz question. How many integrators will be in the block diagram of a nth order system? N number of integrators. As many states, that many integrators. Because states are having only first order ODE dynamics, not second order or third order. First order ODE dynamics. Each state is having its own first order ODE dynamics. So that's why only one integrator is enough. At the input of the integrator x dot, at the output of the integrator x. That's all. Here it is written in a combination fashion. So this x is a vector actually. So that's why the input, at the input the arrow is a block arrow, just to represent that it is a vector, a block arrow. Then you can see, you can read through the equation and you can read through the block diagram, it matches pretty well. So as you can see, x dot at the output of the summer must be equal to the input of the summer. So x dot equals to a into x, a into x. So let me take out the pointer. X a, so a into x plus b into u, ax plus bu equals to x dot, equals to x dot. So x dot equals to ax plus bu. So this is satisfied. Y equals to cx, c into x, cx plus d into u. This u is flowing through d, d into u is y. So for every equation, actually there would be a summer. Every equation there would be a summer. At the output of that summer, you write the LHS of the equation, which is the variable. Maybe it is y, maybe it is x dot. So at the output of the summer, you will write this x dot and y. Input of the summer, whatever is in RHS, you have to construct that using ideas of block diagram. So you have constructed it. You have taken the signal, passed it through whatever is necessary to be passed through. So these blocks, block gains A, B, these are the matrices you have passed through. You have passed the signals to them and you have constructed the output. Very simple block diagram. You should remember this block diagram. How to obtain the state space realization? So we are talking so much now about the state space realization. Also we saw the state space as a diagram as well, and I am telling you that when we model, so we need to have some information about the states. So these things are necessary in order to obtain the state space realization. We need to know the evolution of the states. X1 dot equals to f1, that f1 function we need to know. So certain things are there to be to know of. So what is that knowledge, or through what knowledge we would be able to construct the state space realizations? That is the question, and with this I think this the lecture will end. So this lecture will end with this question and some pointers to the answer of it. So how we are supposed to construct the state space realizations? Of course, if you have the system knowledge, that means the knowledge of the system dynamics, you will be able to construct the state space realizations by understanding which you can term as the internal states, what is the output. It is very clear in front of you, as in the examples I already showed you, in the example videos I already showed you. In the next lecture we will start with this. We will see simple systems and we will derive the state space realizations from those systems, and you will also be given tutorial sheets to solve state space realizations for given systems. Next, from where we can obtain state space realization, if you already have a transfer function, and this works only for LTI systems of course, if you already have a transfer function, you can construct a state space realization from that transfer function. So this is also something which is very important and we will look into. Another way from which we can come to state space realizations is through block diagram representation. So if you have a system already represented in block diagrams, you will be able to derive the state space realizations, and hopefully you already have some hint how to do this, as I discussed in the last slide, integrators and gain blocks and summers. So anyway, those that will be also be taken up in detail. So if you have a block diagram representation, you can create a state space realization, and all this not the system dynamics, but the other two works the other way around also. So if you have the state space realization, you can obtain a transfer function, obtain the transfer function. If you have the state space realization, you can obtain a block diagram, that also you can do. So also there is another important thing in this slide, which is the definition of state, and with this we will end. So we are talking about state. So almost we have an idea, but let us formally define the state. So it is the minimum information at some initial time t0 which is needed together with knowledge of the control input for all times t greater than t0 to predict the behavior of the output of a dynamical system for all t greater than t0. So in order to predict the output of a dynamical system, we need the knowledge of the input obviously, but we need the knowledge of, we need information of some other thing also. So those other things, so those other information and the minimum amount of information that we need, and we need that information at the initial time only, at t0 only, we don't need it further. As you have already seen that state space realization, we know the evolution of the states, so the information that we need is only the initial condition of the states. So that is the information we need. So the minimum information we need. So if you need if there are n number of states, we need n number of information of those n initial conditions. So that is the minimum information. So those variables whose initial conditions we need to know are termed as the states. Those variables whose initial conditions we need to know are termed as the states. So this is the minimum information at t0 which is needed together with knowledge of the input for all t greater than t0 to predict the behavior of the output of a dynamical system for all t greater than t0. So this is what is meant by the states. Now, one thing I would like to point out before ending the lecture, suppose I have in a system I have two states, x1 and x2. If I construct another another state x3 as x1 plus x2, am I adding anything useful to the system? Am I adding any useful information to the system? No, because by knowledge of x1 and x2 I can always calculate x3. x3 is not independent of x1 and x2. That independence need to be there. This is not generally highlighted even in the definitions you will see. However, when we say minimum information, it implicitly means that these minimum set of information are independent of each other. So these x1 and x2 are also independent of each other. That's why they form an orthogonal basis. As you saw in the state space, they form orthogonal basis. x1, x2, if there are n number of states, they form and they form a n dimensional state space with n number of orthogonal vectors. So they are all independent of each other. If one vector is orthogonal to another, their dot product becomes 0. That means they are orthogonal, and that also means they are independent of each other. So this orthogonality is important. So the knowledge of one must be entirely independent of the knowledge of the other. So the evolution in one direction must be independent of the evolution in another direction. Only then these variables, if a internal variable, if the set of internal variables satisfies this condition, suppose you have a set of internal variables x1, okay, there is some problem in the writing, x1, x2, xn. Suppose you choose these n variables, you have to be careful that all these n variables are independent of each other. So one x3 like this is not included here in this set of variables that you have chosen. If x3 is x1 plus x2, you must remove that x3. x3 must be independent of all other xi's. So any xi must be independent of all other xj where j is not equals to I. So this is how technically or formally it can be defined. However, we may not go in so much into that. I hope you understand what I try to mean when I say that every state variables that you choose must be independent of each other, and if there is another state variable which is also independent of these n, that should also be included. So if there is an xn plus 1 which is independent of this n number of variables, it should also be included in this set. So we must include all possible independent internal variables within this set. Only then we will have a complete description. Otherwise we will not have a complete description. We will have incomplete description. So two things one need to be careful. No state variable must be dependent on any other state variable. Even if x3 is x1 plus x2, why x1 plus x2? Just x1. Then why we don't need to repeat x3, right? If it is 2x1, then also we don't need to repeat x3. If the knowledge of x1 is sufficient. So like this. So all the state variables, so the variables will be called state variables only when they are independent of each other, and any other independent internal variable, any other independent variable which contributes to the dynamics of the system, any other internal variable which contributes to the dynamics of the system must also be included in the set of state variables, in the set of state variables, that should also be included. So one has to be careful when one is constructing the state space realization, mainly when you are doing it from the system dynamics, because you have to understand how many internal variables are there which are independent of each other. You should not take one variable which is dependent on another variable in some way or the other. If from transfer function and block diagram, we don't need to be so much cautious because there is a very direct relationship and we understand it very easily. However, from system dynamics, we actually need to assign some states, and we need to identify states, and this requires some degree of skill. So we need to be a bit careful here. So with this, I will end the lecture for today and see you in the next day, where we will begin with construction of state space realizations.